So welcome everybody. It's my pleasure to introduce Anne-Sophie Kaloghiros, who's gonna from the University of Brunel, who's gonna talk on a joint problem, one-dimensional moduli spaces of Fano threefolds.
Okay, so thank you very much for the invitation to speak at ZAG. I'll talk about a joint project with Hamid Abban, Ivan Chertsov, Dongchen Jiao, Jesus, who's the host, and Theo Papazachariou. So in a sense, what I want to discuss today is yet another consequence of the general correspondence between differential geometric properties and algebraic geometric properties of Kähler manifolds. So in a sense, the prototypical result of this type of correspondences is the uniformization theorem, which I want to use as well as some sort of intuition for what I'll talk about in this talk. So essentially, for genus G greater than 1 Riemann surfaces, this uniformization theorem tells us that the existence of a unique conformal metric of constant scalar curvature -1 is equivalent to the existence of an embedding as a GIT stable algebraic curve. And what's more is that this correspondence also extends to a correspondence between the constructions of compactification of moduli. So it extends to compactifications of moduli spaces. So here, the compactification that's constructed by degenerating metrics on the differential geometric side, and the one that's constructed by degenerating stable curves, so the Hilbert-Mumford compactification of the moduli space of genus G curves, correspond to each other. So here, what the reason why I brought this up is that essentially it's a very common procedure, at least on the differential geometric side, to construct moduli spaces for spaces endowed with special kind of metrics. So what I want to talk about today is an instance of this correspondence in the case of Fano varieties. And this says essentially, so the first step in this is essentially the following result by Chen, Donaldson, and Sun, which says that if X is a Fano manifold, then it admits a Kähler-Einstein metric if and only if it is K polystable. This is the proof of the so-called Yao-Tian-Donaldson conjecture, and was extended to the singular case by Li, Wang, and Xu a few years later, in a statement that says that if X is a Q-Fano variety with a Q-Gorenstein smoothing, then it admits a singular Kähler-Einstein metric if and only if X is K polystable. Now, Kähler-Einstein metrics are canonical. So in a sense, in what I said just before, we could imagine that they could be used to construct moduli spaces. And until very recently, the moduli of Fano varieties was thought as being very pathological. So this is because common techniques to construct moduli spaces of higher dimensional varieties just didn't work in that case. So Giza stability didn't work because we couldn't embed asymptotically ordered generations. Koller, Shepard, Barron, Alexeyev methods of moduli of stable varieties didn't work because they were based on the minimal model program, and we obtained non-separated spaces in this case. So, but it turns out that, and that's probably one of the most impressive, in my view, consequences of this whole theory of K-stability is that the existence of this canonical metric or K polystability, if you like, is the right notion to build a well-behaved moduli space for Fano varieties. And so here, the result, so this result is really based on the work of many people and on a number of papers. I hope I won't offend anyone by just quoting those two papers, Li Wangshu and Xu Zhuang. But this is based on a lot of work that has been going on in the past few years. And this result states that there is a projective moduli space, MNV K polystable, so whose closed points parameterize K polystable Q Gorenstein smoothable Q Fano varieties of dimension n and volume V. So here Q Fano varieties means Fano varieties with KLT singularities, and Q Gorenstein smoothable is another technical constraint that says that they have a one parameter smoothing that is Q Gorenstein. So it makes sense to define a canonical class on the smoothing. So now that we have this result, I'd like to turn to some explicit cases, because so before I start with this, let me say that the original definition of K-stability, which I won't recall here, is in terms of numerical invariants that are associated to test configurations So if you like, one parameter subgroups in the general linear group of pluricanonical or global sections of pluricanonical devices. And this is a very analytic notion. One of the reasons why, so since then there's been these valuative criteria which were due to Fujita and Lee originally, which have reformulated K-stability, or which have given criteria for K-stability in terms of invariant, in terms of valuative invariance. I'll just give one example here. So the beta invariant, so if X is a Fano variety in our case, then a divisor E over X is a divisor on some model of X. So we have a variety X tilde with a proper map to X. and E appears as a divisor on X tilde, not necessarily on X, then the beta invariant of E is this valuative invariant, which is defined as the log discrepancy of E minus an integral from 0 to infinity of the volume of f upper star of minus kx minus te dt. So I'm not saying, I'm not pretending that this invariant is easy to compute, but I'm just trying to illustrate that this invariant, that birational methods can be used to compute this invariant in many cases. So, and so what Fujita and Lee have shown is that X is K-stable or K-semi-stable. If and only if the beta invariant of E is strictly positive or greater or equal to 0 for all divisors over X. So what I was hoping to illustrate here is that birational geometry techniques are very useful in computing these invariants. So let me discuss a little bit the application of this theorem above on the projective moduli spaces to Fano threefolds. So Fano threefolds. So what we know is that there are a finite number of smooth Fano varieties in each dimension, and we know more in small dimension. There are 10 del Pezzo surfaces, so smooth del Pezzo surfaces. And there are 105 Fano threefolds, which were classified by Iskovsky, Mori, and Mukai in the early 80s, late 70s, early 80s. For dimension greater or equal than 4, there's no classification, but we still know, we still have the boundedness. There are some example known. And so here, what I should say is that this classification tells us a lot of information about the varieties we're looking at. So these classifications are in terms of contraction maps that the Fano might have to other projective varieties. So I'll come back to that. But examining basically this list of 105 Fano threefolds or deformation families of Fano threefolds, my collaborator and I studied the K polystability of the general members of each of the 105 families of Fano threefolds. So here I refer to Fano project, this preprint with Araujo, Castavet, Cheltsov, Fujita, me, Jesus, Shramov, Zeus, and Viswanathan, which basically is called the Calabi problem for Fano threefolds. And in there, the main theorem that we prove is that if X is the general member of one of the 105 family of Fano threefolds, then either X belongs to a special rogue family, family 226 in the Mori-Mukai classification, which I'll come back to in a bit, or X is divisorially unstable. And divisorially unstable here means that it is it fails the valuative criterion for K stability in the most obvious way. So there is a divisor on X, not just over X, on X with a negative beta invariant. And so Fujita classified all such divisorially unstable general members of Fano threefolds and found that there were 26 families. So here, either X is in this family MM226, or it's divisorially unstable, or it is K polystable. So in particular, K polystable general member is equivalent to K semistable or to divisorially semistable general member for Fano threefold, if you're not in case of the family Mori-Mukai 226. So let's consider a deformation family with K semistable general member. And so here, the reason I say K semistable is that it turns out that 226 also has K semistable general members. So here this is basically one of the families which are not divisorially unstable. Then it makes sense to discuss the K modulate space or the K moduli compactification of this family. So this is going to be a component of the space of the projective K moduli space that appears in Li Wangshu and Xu Zhang's theorem. This is a component of M3K polystable. So 3 is the dimension and the volume is minus KQ. So the question I want to ask is, what do we know for these? And can we study some of these explicitly? So maybe let me mention some previous work on these. So there are few cases where the K moduli space has been studied explicitly. So I suppose the first case, which predates all of that, is the Mabuchi-Mukai study of Delta 4 surfaces. Then Odaka, Spotty, and Sun generalized this to and constructed moduli spaces for del Pezzo surfaces. And then in recent years, Liu and Xu, sorry, have studied cubic threefolds from an algebraic geometric point of view, while Spotty and Sun, taking more of an analytic approach, have studied cubic n-folds and degree 4 del Pezzo n-folds. And then there are, I think I should mention as well, Theo Papazatariu's study as well, which I'll refer to in a little bit. Okay, so which he talked about in a ZAG seminar about a month ago. So essentially, the question I want to ask is, can we use the classification of Fano threefolds to describe the K moduli spaces? So somehow here the issue with you could say we have the classification, so we know everything we want to know. But the problem with this classification is that it's far from being modular. It gives you a recipe to construct those Fano threefolds, but it doesn't tell you when two Fano threefolds constructed with that construction are going to be isomorphic to each other, for example. And also, it does not give you a picture of degenerations of the smooth Fano threefolds, of K polystable degeneration. So let's start with the easy cases, which should be easier to describe. And the first type of easy cases is that we have 44 families with zero-dimensional moduli in the classification. Out of these 44 families, only 24 have K polystable general members, or are 226. So in a sense, I won't spend much time discussing the ones that are not Mori-Mukai 226, because here the picture is pretty clear. And then we have 8 families with a one-dimensional moduli, out of which 6 have K polystable general members. And I'll talk a little bit more about these. But let me start by giving the explicit description of K moduli spaces of some K moduli spaces of these Fano threefolds. So let me start with the zero-dimensional moduli of this pathological case. So here, let me look at an element of this deformation family, Mori-Mukai 226. So if we look at the classification, it tells us that X has 2 extremal rays. The contraction of one of the extremal ray is the blow up of a line in V5, the Del Pezzo threefold of degree 5. And the other extremal ray is the contraction of a twisted cubic curve in P3. So perhaps here I should say that this space V5 here has been studied a lot. It has rich connections to representation theory. We know a lot about this space. It's a linear section of a Grassmannian 2-5. And in particular, we know that there exist 2 types of lines on this threefold. There are the lines that have balanced normal bundle, with normal bundle isomorphic to O plus O. And there are the unbalanced lines, which have normal bundle isomorphic to O minus 1 plus O1. And so this tells us that we have 2 members in this family. So let me discuss the first one, which I call X1, which is going to be obtained from the blow up of a balanced line here, number 1. So we know that when we blow up a balanced line, then we have an effective GM action on X. And X has a degeneration to some, call it X1. X1 has a degeneration to some X0, where X0 has the action of a 2-dimensional torus. So it's a complexity 1 T variety. And it's singular. So so it's not isomorphic to X1, which tells us that before I say this, I should say as well that we can show easily that X0 is K polystable, because there are some almost combinatorial criteria for complexity 1 T varieties. And it follows that X1 is strictly K semistable. It is K semistable because it has a degeneration to a K polystable Fano variety, but it is strictly K semistable because it is not isomorphic to this variety. Now let's look at the second member of this family, and the second member is a little bit more tricky. So if I call H the unique hyperplane section of my quadric in P4 that contains my twisted cubic, in this case, when we've blown up a non-balanced line, it turns out that H is singular. It has exactly 1 singular point. which I call P0. And the automorphism group of X has a non-reductive part, which forces X. So here this is X2. So X2 cannot be K polystable. This is essentially a result showing that a K polystable funnel always has reductive automorphism group. So it is not K polystable, but in fact it goes a bit further. If we call Z the inverse image of this singular point, and we blow up this to obtain a divisor E, then we find that the beta invariant of E is negative. So actually, X2 is
we stopped hearing you. I don't know if I'm the only one. It's me. Okay, now I see, but I don't hear. I don't hear. Do you hear me? No. You could try disconnecting the sun and connecting it again. Maybe that would work. I think it got screwed up when you got a phone call or something. I hear nothing literally, but the problem is.
Can you hear me now?
Now I do, yeah.
Okay, many apologies.
So I don't know if everyone was in the same situation because I put it on the chat, but no one replied.
Yeah.
So let me see what this went down when someone called you. I'm trying to remember where you were.
I think I was discussing X2 being
polystable. I think that was the last thing at least that I managed to process.
Okay, so what I said after is that in fact, if we blow up the fiber over the singular point P0, which lives in here, or on the hyperplane here, not on gamma, then we find a divisor which actually has negative beta invariance. So that actually X2 is not just non-K polystable, it's non-K semistable. So here what we have is that we've got, you know, as a conclusion, what we can say is that the component of this moduli space M3, so this has volume 34 KPS, that corresponds to family 226 is basically is just this point x0, which is not itself a smooth Fano in family MM226, but it has a Q-Gorenstein smoothing to a smooth Fano in family MM226. So basically, when we look from the point of view of K stability, X1 still appears as a K semi-stable Fano degenerating to this point here, X0, but X2 completely gets forgotten by the K moduli space. Okay, so let me discuss some of the dimension of the families that have dimension 1 of Fano moduli. And here the general approach will be to use the classification to try and come up with a parameterization of smooth K polystable Fano varieties in that family. So this should give us a sort of family over a affine curve C, hopefully. And then the method is to try and compactify the family in an ad hoc way, or compactify the family over a compactification of C. And then if we obtain this, then we have a dominating map from C bar to the component of moduli which corresponds to that family. And so in some cases, we might even be able to understand this map. That is to understand, essentially when two fibers, X bar S and X bar S prime are isomorphic for S and S prime in this affine curve, in this curve. But yeah, in not necessarily going all the way to this. So the first example that I'd like to briefly discuss, because this was discussed by Theo a month ago, and this is Theo Papazachariou's result, is this example of family 225. So family 225 is a Fano threefold, which is obtained either by blowing up a curve, which is an intersection of two quadrics in P3, or as a pencil of quadrics over P1. So now, if we look at the picture a little bit, calling the two quadrics S and S prime. So I say that S has an equation Q of X and S prime has an equation Q prime of X. I call gamma the intersection of S and S prime. And then the corresponding pencil of quadrics essentially sends a lambda times Q, a hypersurface in P1 cross P3 with equation lambda times Q of X plus mu Q prime of X equals 0, where lambda and mu are coefficients on P1 and X is the coordinates on P3 to lambda mu. So this is the picture that is given to us by the classification of Mori and Mukai. And so here, the intuition is that we gain from this classification is that all of the geometry of X, if you like, is contained or is the geometry of, depending on what your personal taste is, either the curve gamma or the pencil SS prime. Okay, so gamma is just the base locus of the pencil. And so here, what Theo proves, theorem, is that actually this component of the K-moduli space corresponding to the compactification of this family 225 is isomorphic to the GIT compactification of the curve gamma, if you like. And this is basically the GIT quotient of the Grassmannian 210 by SL form. So this Grassmannian 210 corresponds to picking up the two quadric hypersurfaces in P3. And so here we know that the points here are either smooth complete intersection curves or the curve x0, x2 equals 0 intersected with x1, x3 equals 0. So which is the intersection of these two degenerate quadrics. Okay. And so what Theo proves is that, you compact it. So essentially, the elements of this family. So if we look at the compactified moduli space, the K polystable Fanos with a cube Gorenstein smoothing to an element of 225 are either the blowups of a smooth 2-2 curve in P3 or the blowups of these quadrangle curves. Okay, so let me now discuss another example, which is or the second example with one dimension, which is the example of family 224. So here, family 224, the classification tells us has two extreme arrays, which are on the one hand a P1 bundle to P2, and on the other a conic bundle with discriminant curve, which is a cubic with at worst nodes. Now, from this description of the extreme arrays of X, we get parameter space description. And we can show that X is a smooth Fano in this. If X is a smooth Fano in this family, then X is either X mu, where the equation of X mu is given here. So this is mu times VW plus U square multiplied by X plus mu times UW plus V square multiplied by Y plus mu times UV plus W square multiplied by Z equals 0. And here this is for all mu in C, mu cube not equal to plus minus 1, which correspond to singular fibers. And then we have another two cases to consider, which don't have such an equation. And these are what I call X dagger and X double dagger, where basically we have VW plus U squared times X plus UW plus V squared times Y plus W squared Z equals 0. And then VW plus U squared times X plus V squared Y plus W squared Z equals 0. And what we can show, and this is already done in the book, is that X mu is K polystable for all mu in C. That is not plus or minus 1. And the two separate cases, X dagger and X double dagger, both degenerate to X mu equals 0. So this tells us that basically X dagger and X double dagger are strictly case unstable. And we have this essentially this parameterization here, X over C minus the cube roots of so C minus mu cube equals plus or minus 1. Let me just write, where all of the fibers are smooth K, precisely the smooth K polystable Fanos in family MM224. Okay, so here the theorem that we proved in So here, this is essentially my first step of the general approach, where I found a family over an affine curve that parameterizes all smooth K polystable funnels. So here we can just forget about X dagger and X double dagger, because we've seen that they are not K polystable, they are strictly K semistable. So in the book, so that was in the book, we showed that all fibers of the pencil X lambda mu, where the equation of X lambda mu is lambda times U square X plus V square Y plus W square Z plus mu times dwx plus uwy plus udz equals 0. So here, the previous curve C corresponds to all parameters of the form 1 mu. So we prove that all fibers of this pencil over P1, so lambda mu are in P1, are K polystable. Funnel threefolds. For mu cube equals to plus or minus 1, and for mu and for lambda mu, sorry, I should have said, so for 1 mu with mu cube equals to plus or minus 1, and for 1, 0, we have singular isomorphic Q-Gorenstein smoothable funnels with a smoothing in the correct family, and so this gives us this. So this achieves step 2. So here this is my family X bar over C bar, if you like. And then this kind of already finishes everything there is to say, because so we know that so we know here. So we know that we have a dominating map to the moduli space, or the component of the moduli space that parameterizes elements of 224. And what we also know about this is that this is one-dimensional. This is necessarily rational because it's unirational and in dimension 1. And because we know the form of the singular K polystable members, we also know that this is smooth, because those singular K polystable members have non-obstructed deformations. So this tells us already that this is just P1. Now let me just mention that my student Dongchen Zhao has shown further, has found the an explicit group G in the automorphism of P1, such that X lambda mu is isomorphic to X lambda prime mu prime, precisely when lambda mu is G times lambda prime mu prime for some G in the group G, and the group G is essentially isomorphic to A4. Okay, so here we have a completely understood picture, and in fact we could have obtained a clear picture which actually corresponds to the same picture by studying the GIT of intersections, hypersurfaces that are intersections of the form 1, 2 inside P2 cross P2 with action of PGL3 times PGL3. So and here we also find that the GIT of hypersurfaces of type 1, 2 and the K moduli picture for members of family 224 coincide. So let me discuss a slightly more mysterious example, which is that of family 222. So family 222 has two extreme arrays. One corresponds to the blow-up of a conic in V5, so still the Del Pezzo manifold of degree 5. And on the other side, P is the blow-up of a rational quartic curve. This rational quartic curve lies on a single quadric surface, which is smooth, so P1 cross P1 inside P3. And here, when we start from this description, from this classification, we can write down a parameter space description. But here, let me just mention that before going any further, I should say that in the previous two cases, so in the case of family 225 and family 222, there was essentially one curve that encoded all of the geometry of X. In the case of 225, it was this 2-2 intersection, which was the base locus of the pencil on the other side. In the case of 224, we have a P1 bundle on one side, a conic bundle on the other. So essentially the only relevant piece of geometric information is in the discriminant of the conic bundle. But here we have two natural curves encoding information on X. The first one is this conic C in V5, and we could try and compare the K stability, the K polystability of X with the GIT stability of C in V5, which has a PGL2 action, or on the other side, there's this 1-3 curve living on P1 cross P1 with action of PGL2 times PGL2. So here what we find is that if X is a smooth Fano in this family, we can assume that X is the blow-up of a curve. So we can write gamma as a curve gamma with parameters A and B. So here I'm using the following coordinate description. So my curve 1-3 lies on a unique smooth quadric, which I write P1 plus P1. So it has coordinates, the first P1 has coordinates UV, the second XY. It's embedded in the natural way into P3. And in these systems of coordinates, I can write my curve gamma as U times X cubed plus A times X squared Y equals V times Y cubed plus B times Y squared X. And what we were able to show in the Fano project is that the curve obtained by blowing up such a curve gamma is K polystable precisely when A is equal to B is equal to 0, or when the product AB is non-zero. So basically the only case to keep out is that of A equals 0, B non-zero, or A non-zero and B equal to 0. So here we show in the current work that we can we reparameterize this curve. Actually, this was already in the book, and assume that A and B are equal by just scaling. And if we look at the family that we obtain when lambda is now allowed to go all over P1, then we find that X, which I now call X lambda, for lambda not 0, not equal to plus or minus 1 or plus or minus 3 is K stable, in particular K polystable. So it is K polystable and has finite automorphism group. That X0, so lambda equals 0, is K polystable. That the two singular fanners that correspond to plus minus 3 degenerate to X0, have a degeneration to X0. So they are strictly K semistable. And then X plus or minus 1 is singular. The corresponding curve gamma plus or minus 1 is a curve. So here in the general case, I had a rational quartic curve. Here I have a line with a cubic. And this gives gamma and hence X a non-reductive automorphism group. So it's definitely not K polystable. But what we can show is that it degenerates. So X plus or minus 1 degenerates to the funnel we obtain taking lambda equals to infinity. So this corresponds to the curve gamma infinity, which is just essentially ux squared y equals v y squared x. And what's this curve? This curve is a conic. So this is the conic ux plus minus vy equals 0. And then two distinct lines that correspond to x equals 0 and y equals 0. And we find that this x infinity is K polystable. So let me just say, so this part for determining K polystability of X lambda of all the smooth ones was proved by Cheltzoff and Park. And the rest is the current project, the current collaboration. Okay, so here what we have is that this gives us essentially, again, a compactification of my family, X bar over C bar. And again, C bar is dominated by P1 and dominates M bar 222. So M bar 222 is exactly as before rational and smooth because we can study directly the singularities of X infinity. So M bar 222 is P1 again. So maybe one remark on this case is that when we consider the GIT picture, for a curve of type 1,3 lying on P1 cross P1 acted on by PGL2. Cross PGL2, then we find that the GIT polystability of this curve is equivalent to the K polystability of X obtained as a blow-up of P3 along gamma. So studying the GIT picture on the left, we do find that essentially the two GIT polystable non-stable elements are correspond to the curve you obtain for x0. So the ux cube equals vy cube, and then this curve corresponding to the conic N2 lines. Okay, so let me and all the other possible degenerations lead to unstable curves. So let me just conclude by giving a few remarks on the other families. So family 312 is pretty much a similar description. So Elena Denisova, who's a student of Vanya Chaltsov at Edinburgh, has studied the K polystability of all smooth members. So we have very much, as in this case, a compactification, a good family over an affine curve, a compactification, and pretty much everything is known. Family 313, we understand the smooth K polystables, but not the compactification yet. That's very much work in progress. Family 413 is also all understood. So that's the 6 families of one-dimensional K moduli space. In all the cases, we understand the modular space is unirational. I don't think that's going to be true in higher dimensions, but I may be wrong. And then there's always a kind of hidden GIT stability picture behind all of these K stability pictures. And that seems to be kind of what you would expect, as in K polystability should be locally GIT in flavor. And so, so here we have just one-dimensional spaces and have some GIT pictures that kind of extend. It's not clear to me, however, why 222 should be the GIT on P1 cross P1 rather than the GIT on V5. So I'll stop here.
Thank you. Do we have any questions or comments? Okay, I have a question. I'm really bad with numbers. I think it's 224, the one where.
Yeah. The 2 conic bundles?
No, no. Yeah. No, sorry, the previous page.
Yeah.
Yeah, there's somewhere where you said your student has actually found the explicit group. Wasn't it that one?
Yeah. So he has found, found generators for the group. So he's bounded above the possible order of the group. And then he found generators and found an explicit description. I'll ask him to send you a...
So my main question was the bit where we say, okay, this is one-dimensional rational smoother for SP1. This argument should apply to whenever the K module is one-dimensional for all Fano threefolds, no?
Yes, because we always manage to find in an ad hoc way a parameterization by some subset of the affine line. Okay, yes and no. Yes, for the rational. Now the thing is that I don't know that the generations of 312, for example, have unobstructed definitions. So in that case, so I think they do, but when I try and study it, are we being recorded or not? Yeah.
Okay, we stop the recording now. Haha, you should have come.
No, that's fine.